Hi guys, welcome to this revision session on moments, a topic that lots of people really don't like. I don't know why. Some people find it a bit tricky. So I want to try and explain it as easily as I can. So what we're going to be doing today is looking at what a moment is, calculating a moment, and applying this thing called the principle of moments in questions. So if we look at this example here, this is a bottle opener opening a bottle of beer. Of course, none of you will know how to open a bottle of beer because you're 16, you would never have done it before. This is a perfect example of a moment. So if you have this thing here, bottle opener, which is called a lever, the lever, if you apply force to it here, what you'll do is you'll cause it to turn. So normally if you had an object on the table, let's say like a book, and you apply a force to it, what you'll do is you'll cause that object, that book, to accelerate in a straight line. Well, sometimes if you apply force to it, you will cause the book to turn, to spin. Now it depends where you apply that force, and depends also if the object's fixed in any way. It depends on something called the centre of mass that you would have done about in your course. So let's have a look at what a moment is in this case. So if you apply that force there, it will cause it to turn around this bit called the pivot. Another example is like a hammer. So you have a pivot here about which this hammer can turn. If you apply a force here, you will be able to cause here a clockwise turning effect. I mean, the easiest example I think of a moment is with a door. So if you have a hinge here, which is the pivot, sometimes they call it fulcrum as well, then if you apply a force in the right place, it can cause a turning effect. Now, this moment, a turning effect of a force, depends on a few things. First off, it depends on the size of the force. So let's say I'm applying a force at B and I open the door. Then let's say that I apply a bigger force, the door will have a greater turning effect. So moment depends on force. You could even say they're proportional to each other. You double the force, you double the moment. It's also dependent on the distance. So if we look at forces B and C, if you apply a force at B and C, let's say that they are the same force, the equal force, you will notice that the door will have a great turning effect if you apply the force at B than at C. And you'll probably notice that even to have a decent turning effect, that you will need to increase the size of your force at C. That's because moment depends on the distance away from the pivot that you apply your force. So if we look at C, that's the distance. If we look at B, the distance is much greater. So moment depends on the size of the force and the distance away from the pivot that you apply that force. But it also depends on one more thing, which is why I've included A. It includes the direction the force is applied. Now, the force, in order to have a maximum moment, the force needs to be at a right angle to the distance away. So if you imagine this here is your distance away from the pivot that you're applying your force, that needs to be at a right angle to have a maximum moment. If you look at this force here, that's the distance away, and technically that there is 180 degrees. Because of that, if you apply a force there at A, you won't really have a moment at all. It won't cause the door to turn if you apply a force like that. So this is where we get this equation from for moments. So moment, force times distance. Force measured in newtons, distance measured in meters, and moments measured in newton meters. And the way we get that is because you just substitute the units into the equation. Newtons times meter, newton meter. Sometimes what they might do is they might give you the distance in centimeters. You may need to change that into meters, but do look at the units, because if you said your distance was in centimeters, then you could have that, and then what you could do is, instead of saying newtons meters, you could say newton centimeters. We've obviously got to see what they want in the question. They may have already given you this unit here, so you may need to convert it one way or the other. Just look out for what it wants and what you're given. So this here in the equation says D is the perpendicular distance from the pivot to the line of action of the force. Again, that just means that that force needs to be perpendicular to this distance measured here. If you do change the angle, it will affect the moment. For example, if you decrease the angle like that, it will decrease the moment. If you make it 180 degrees here, then the moment will be 0. So really basic question here, just to give you an example. Substitute the values in. So the force is 50 newtons. That's good, we don't need to change it. 4 meters away, don't need to change it. 4 times 50, 200. And because we did this in newtons and meters, that will be Newton meters. So here are some examples. We're going to pause the video. Well, no, feel free to pause the video and I'll reveal the answers and go through them in a second. Okay, first one, nice and straightforward. Force times distance, that's going to be 100 times 2 is 200 Newton meters. The second one, if we do the equation again, moments is force times distance. This time we're given the moment, 150 Newton meters. We're not given the force, so let's just call it F, and the distance is 3. Now this is just some generic algebra, stuff you normally get in maths. 150 is F times 3. I want to find out what F is. So we need to rearrange this equation. If we divide both sides by 3, what that will do is it will change this side of the equation to that, force, which is what we want. 150 divided by 3 is 50 newtons. And that's it. Now this last question, the answers come up already if you've seen that, but the last question, this is the type of question that they're going to be asking you. It's about more than one moment being applied to a situation. So we've got a seesaw here. It says student A weighs 500 newtons. Remember, weight is a force. Student A, 500. And is 2 meters away from the pivot. Student B has a weight of 250 newtons. How far away do they need to be in order for it to be balanced? Right. So this is where we bring in this thing called the principle of moments. So the principle of moments says, and I'll put this on the screen in a bit, that if you have a situation that is balanced or in equilibrium, i.e. like the seesaw, that is because the sum of the clockwise moments equal to the sum of the anti-clockwise. So if person B is sat down on this seesaw and they're applying a force here, they're going to be causing the seesaw to turn that way, clockwise. If person A is on the seesaw, they're going to be causing it to turn anti-clockwise. Because the system is balanced, it's in equilibrium, we can say that the anti-clockwise moment is equal to the clockwise moment. Just be careful, because sometimes they will put more than one moment in this, hence why it says the sum of the clockwise and the anti-clockwise. So what you can do is this, you could say moment clockwise equals moment, I'm running out of room, clockwise. So let's talk about the moment clockwise. Well, the moment clockwise is force times distance, and the moment anti-clockwise is force times distance. If you want, we can call it the force clockwise, the distance clockwise, something like that, just so you know what's what. So clockwise is person B here. The force is 250. We don't know what the distance is, so let's just call it D. The anti-clockwise is 500 times 2. So again, just be careful, you may need to change meters, centimeters, etc. So let's simplify this before we start rearranging. 500 times 2, well, that's just 1,000. Nice and easy. We don't know what 250 times D is, but we just got some generic algebra. We want D on its own, so let's divide this side by 250, and we'll divide this side by 250. If you divide this side on the left by 250, we get rid of all this, and you get D equals 1,000 divided by 250, which is equal to 4 meters. Write down every single stage of what you do, even if it's just this thing up here or stating the principle of moments, could gain you a mark. Just make sure as well, what they could possibly do in this type of question is they may tell you the mass of the person. So remember, mass is measured in kilograms. Therefore, you need to convert that into weight, which is a force. And the equation for that is weight is mass times gravitational field strength on Earth, 9.8. So, principle of moments is this, as I said, the sum of the clockwise moments about a point is equal to the sum of the anti-clockwise moments. When the object is in equilibrium, it's balanced. just like the seesaw. So if I just take you to one final question, this one is a real tricky one. This is an A-level question. In fact, if they were to ask you something like this, you're having a bad day. But let's see if you guys can do it. I'm just going to give you guys a second. We want to pause the video, work through it, and then I'll work through it with you. Okay, so let's go through this. Now, it's really nice here that they've actually given you a bit of a simplified drawing of what's happening. I always say that if you do get a drawing like, I don't know, this arm here, and you're thinking, I don't understand what's going on, try and simplify the drawing like they've done for you, and it will really help out. So we've got a few forces acting here. We've got the weight of the forearm going down. You've got the actual weight here, which is 80 newtons on their hand going down, and you've got the force applied by the bicep. So at the minute, this person's arm is balanced. So what we can say is that the moment going anti-clockwise equal to the moments clockwise. Now just remember the sum of the moments, because here going clockwise, caused by the weight of the forearm and this weight itself, those two are going clockwise, and you've got the moment going anti-clockwise, which is the force of the bicep. So let's have a look then. The moment anti-clockwise, which is the force by the bicep, we don't actually know the force of the bicep, so let's just call it F. But it says that it's 6 centimeters away from the elbow, which is the pivot. So force times distance for this moment here is equal to the force times distance of the arm plus the force times distance of the weight or the load. So let's substitute some numbers into it. We don't know the force of the bicep. What we do know is the distance is 6 centimeters. So let's change that into meters straight away. To do that, you divide it by 100, so that would be 0.06. Apologies for this, my pen keeps doing that. There we go. The force of the arm and the force of the weight. So let's talk about the actual force of the arm, which is the weight of the arm. That's 20 times 15 centimeters, which is 0.15. Even little things like this, doing the little conversions, if you can do them separately, that's good, but they're worth marks. If you have no idea what to do in the question, but you see something that needs changing like that, do it, because you may get a mark even though you think I've got no idea what to do. Plus, it says that weight is 80 newtons and the distance is 35 centimeters, so change that to meters, will be that. Take your time when you're doing this sort of thing. You don't need to rush it and do all these calculations yourself. Let's rewrite it once more. F times 0.06 is 20 times 0.15. So if you do 20 times 0.15 in a calculator, you get 3 plus 80 times 0.35, which is equal to 28. Now the moment caused by that weight that this person's holding is very, very large, because the distance is more than twice that of the other one, and the weight itself is 4 times as much. So it does look a massive amount. So I'm just going to rub out some of the workings up here so we've got a bit more room. Okay, so let's simplify this a bit more. We could say that F times 0.06 is equal to 31. All I've done is just add them together. And then again, back to the simple algebra. F times 0.06 is 31. So if we divide this side by 0.06 and divide this side by 0.06, we should get the answer. That will cancel out. So giving us F is 31 divided by 0.06, which is equal to 516.6. Now if we do this to 2 sig fig, we get 520 newtons. Now that seems like a massive amount of force that the bicep is applying. 520 newtons when all you're doing is you're carrying a weight of 80 newtons and your arm is 20 newtons, so a total weight, if you like, of 100 newtons, and yet the bicep is applying a force of 520 newtons, 5 times that. Why does it need to be so much? Well, it needs to be so much because the bicep is applying a force at such a short distance away from the elbow, the pivot. So it needs to apply a massive force to counteract that moment, because remember, these forces are causing that arm to turn. And you could say, well, why don't we just increase, to reduce the force on our muscles, why don't we just move, why can't it be that we've evolved so that that pivot is maybe a bit further away from where the bicep's attached? Well, then you won't get as much movement in your arm when you move it, plus the bicep's going to be in the way. That's the beauty of our arm. It can open up by 180 degrees or so. So that is the most complicated question you're going to get, but that's the type of thing they're going to do. They're going to involve the principle of moments, probably a seesaw is my guess they're going to do. Hope you've enjoyed. See you next time.